All right, let's jump right in. We're going to talk about something that's like a cornerstone of computer science, tree traversals. Seriously, if you're dealing with data structures, you're going to run into trees, and you absolutely need to know how to walk through them. This is the playbook.
Okay, so take a look at this. You've got this tree structure, right? It's not like a simple list where you just, go from one element to the next. So how in the world do you read every single item here? And not just read them, but do it in a consistent, predictable order every single time. That's the puzzle, and tree traversals are the solution.
So, first things first, Section 1. What does it even mean to read a tree?
Yeah, with an array or a list, it's easy, right? There's always a next element. But a tree, it branches out all over the place. That's where our traversal comes in. Think of it as a GPS for your tree. It's a systematic procedure, a set of rules that make sure you visit every single node exactly once. No getting lost, no visiting the same place twice.
Now, when it comes to navigating a tree, you've basically got two main game plans. You can either go deep or you can go wide. So let's talk about depth versus breadth.
Okay, let's break these down. First up is Depth First Search, or DFS. The name kind of gives it away, right? You dive deep. Imagine you're in a maze. You pick one path and you follow it as far as you can possibly go. Once you hit a dead end, then you backtrack and try another path. The other approach, that's Breadth First Search, or BFS. This is totally different. Instead of diving deep, you explore everything at your current level. Like, you check all the rooms on the first floor before you even think about going up to the second floor.
So, let's stick with that deep diving approach for a bit. It turns out there isn't just one way to do it. There are actually three main flavors of depth-first traversal. I like to call them the depth-first trio.
First up, we've got pre-order traversal. The rule here is super simple to remember. Node, then left, then right. That's it. Node left, right. Think of it like this. You visit the parent before you explore any of their children. You process the root of any subtree first.
So if we run pre-order on our example tree, this is what we get. See that? We start at the root, node 1. That's our node. Then we go all the way down the left side. 2, then 4, then 5. That's the left. Once that's all done, we backtrack and go down the right side. 3, then 6, then 7. That's the right. Node, left, right. Make sense, right?
All right, number 2 in our trio is in-order traversal. The rule just shuffles around a bit. Now it's left, node, right. So what does that mean? It means you explore the entire left side first, then you visit the parent node, and only then do you head over to the right side. The parent is visited in between its children.
And if we apply that to our tree, look at the output. We go all the way down the left, we hit 4. Then we come back up to the parent, 2. That's our node. Then we go right to 5. So that's our left node right for that little subtree. We keep doing that all the way up. See how the main root, node 1, is right in the middle of the output? That's the in order for you.
And the last of our trio, you guessed it, post-order traversal. The pattern here is left, right, node. The name post means after, right? And that's the key. You visit the parent node after you visited its entire left side and its entire right side. It's a totally bottom-up way of thinking. You deal with all the kids before you deal with the parent.
Let's trace it. See this? We get 4 and 5, then their parent 2. We get 6 and 7, then their parent 3. Only after both of those big branches are done do we finally get to the main root, node 1. It's always the very last one to be visited in a post-order traversal. Pretty cool.
Okay, let's talk about performance. How fast are these? Well, the good news is all three of our depth-first traversals are really efficient. They all run in what we call ON time. All that means is that the time it takes is directly proportional to the number of nodes. You touch each node once, so that makes sense. And what about memory? The space they need is O to H, where H is just the height of the tree. So for a reasonably balanced tree, that's super efficient.
All right, we've done our deep dive. Now it's time to switch gears and go wide. Let's move on to the level-by-level approach, breadth first search, which you'll almost always hear called level order traversal.
Honestly, this one is probably the easiest to understand. It's exactly what it sounds like. You visit the nodes one level at a time. You start at the top, the root. Then you visit all of its children on the next level, from left to right. Then you go to the next level down and do the same thing. It really is just like reading a page in a book, top to bottom, left to right.
And if we look at our example tree, the output is just intuitive. You get 1, then you get its kids, 2 and 3,
Then you get their kids, 4, 5, 6, and 7. The output is literally just the numbers in order. Couldn't be simpler.
So what's the cost? Time-wise, it's the same as DFS, O of n, because we're still visiting every node just once. But the memory usage, the space complexity, that's where things get interesting. It's O of W, where W is the width of the tree. Why? Well, the algorithm has to keep track of an entire level of nodes at once. So if you have a really wide, bushy tree, this approach can eat up a lot more memory than a deep dive.
Okay, so we've got 4 different methods. The million-dollar question is, which one should you use and when? Let's get practical.
Think of these traversals as different tools in your toolbox. Each one is perfect for a specific job. Pre-order, that's your go-to for making an exact copy of a tree because it preserves the structure. In order, we'll get to this more in a second, but it's the magic trick for getting a sorted list out of a binary search tree. Post-order, this one is perfect for deleting a tree. Why? Because you have to delete the children before you can delete the parent. And level order, or BFS, anytime you hear shortest path, like in a GPS finding a route, you should be thinking BFS.
Okay, I want to take a second to bust a really common myth. This is one of those questions that trips people up in interviews all the time. Does in-order traversal always give you a sorted list of numbers?
The answer, and you gotta remember this, is a big, fat no. It does not. An in-order traversal only produces a perfectly sorted list on one specific type of tree, a binary search tree, or a BST. That's a tree with a special rule. Everything to the left of a node is smaller, and everything to the right is bigger. On a regular old binary tree like the one we've been using, the in-order output is, well, it's just a sequence of numbers, not sorted.
All right, let's do a super quick recap. Key takeaways. For depth first, remember the 3 magic words. Pre-order is node left right. In-order is left node right. Post-order is left right node. For breadth first, just think level by level. They all take O of n time. The big difference is memory. DFS needs space proportional to the tree's height, while BFS needs space for its width. And please, please remember, in-order only sorts a binary search tree.
And I'll leave you with a little brain teaser to chew on. We've spent this whole time learning how to flatten a tree into a list. But could you do the reverse? If I gave you 2 of these lists, say the in-order and the pre-order outputs, could you piece them back together to rebuild the exact original tree? Think about it. That's when you know you've really mastered this stuff. Thanks for tuning in.